Okay, we're ready for part 2. We just did part 1 is uploading now, so part 1 was done for this exam Tuesday 9th of January 2024, so very recent exam for the Edexcel International A-Level in Physics, Unit 4, Further Mechanics, Fields and Particles. So if you watched the first video, I'm now preparing the second video. Part 1 on YouTube went from questions 1 to 16, that's the multiple choice, and the shorter of section B, the shorter questions in section B. Part 2, we'll try and see if we can do it all in one go, but these are longer questions. So, as we said, we managed to finish question 16. This is now question 17. And again, this video is for people who did this exam in January and would like to know what they did wrong or how they could improve their answers using my handwritten answers as you saw in part 1. Okay, so a model aeroplane moves in a horizontal circle. Okay, the path of the model aeroplane is a circle of radius r, shown here, with center at O. So we're going to look at that in a moment in more detail. The dots on the diagram, dot 1, dot 2 I've called them, represent two positions of the model aeroplane as it moves with a constant speed v. Okay. So it moves between two positions, and I've said in time delta t, so there's a short time between there, and we need this delta t to be small for to be able to derive what they want us to derive, which is the accelerations equation for circular motion. Okay, so this is the view from above. Velocity 1, initial velocity, velocity 2, position 2, second velocity. So I'm assuming the plane is going round this way. Doesn't really matter as long as it's consistent. They want you to derive the equation for centripetal acceleration, which is a equals v squared over r. Some people call it centripetal, I call it centripetal, by considering the velocity of the model aeroplane at these two positions, v1 and v2. So I've drawn it as two vectors, v1 and v2, and I've tried to make the arrows of equal length. So your answer should include a vector diagram. So these are the vectors, but I haven't drawn the vector diagram up there. Your answer should include a vector diagram because the change in velocity is vector 2 minus vector 1. So it's changed. So v2 minus v1 will give you the change in velocity. And if you do it that way, with the arrows exactly in the directions as shown in the situation that they're going in, if you do v2 this way and then take away v1, which is a negative arrow of v1, so you're adding the negative velocity, you'll notice that the change in velocity is actually from position 1 almost down towards the center of the circle. Okay, so it shows that the change in velocity is pointing towards the center of the circle, which is what we mean when we're talking about centripetal acceleration. It means the acceleration or change of velocity is directed towards the center of the circle. Okay, so I think that's an important first point to make, that this is what we're trying to show. Okay, so I've said C dotted lines drawn between points 1 and 2. Okay. Oh, I see. I've drawn these dotted lines here to show that these, at 1, the distance from O to position 1 and the distance from O to position 2, those dotted lines are equal to the radius of the circle as well, because we're going to use that as similar triangles. I think it's the easiest way of doing this derivation. So I've drawn these dotted line between points 1 and 2 in the diagram to show that this is also delta theta, and in the vector diagram it's a similar triangle. The delta theta will be the same between the two velocities in the vector diagram here. Okay, it's going to help us. So we have similar triangles, one with two radii and the kind of the distance between positions 1 and 2, which would be an arc length on a circle. Yes, and remember that the arc length on a circle is the equation S equals r theta. Okay, so we're using d theta as these angles. So this angle here is also d theta. Okay, so here would be the arc length, the distance between 1 and 2 would be ds, because we're using that, and theta would be delta theta or d theta. So this is the same equation as arc length. Okay, so from the similar triangles, we have one which is looking at the arc length. And remember, if we're talking about very small times, that arc length is the same as a triangle. So basically, so is this a triangle? And so is that a triangle, because we want time to almost go down to 0 for this mathematics to be correct. Okay? So I think we already got some marks by doing the vector diagram, certainly is 1 mark. Yeah? So then you've got a similar, for small angles, delta theta is equal to V over delta V. Now either of these, or both of these, V1 has a magnitude of V. So delta V over V is also delta theta. So now we've got 2 equations with delta theta in them. One from the vector diagram and one from the situation diagram with the radius and the arc length. Okay, so we have 2 equations. You can now equate equation 1 and equation 2. If you equate them, the 2 delta thetas must be equal. So dv by v and ds over r, where delta s is the velocity. It's a distance traveled between 2 dots, a small distance at the top of the circle here. That small s is obviously the velocity times the time taken between points 1 and 2, which I've already put in there for ease of understanding. Okay, I hope that makes sense to you. So delta s is v times delta t. Okay, so that means we could replace this with this equation if we wanted to, which is what we do the next step. So we then got dv over v on one side, and then we got v delta t or dt over r. Okay, now you'll notice that all you've got to do is to bring the delta t on one side. So dv by dt, as you know, is acceleration, and then the v goes on the other side, multiply both sides of v, is v squared over r, which is what they asked you to prove. This shows that because a is dv by dt, that you have proven the answer. Okay, so if you look at the mark scheme, they have alternative ways of doing this answer. Yeah. So I'll show you the mark scheme so you can have a look at it on the video at your leisure. So this is how they've done it. Yeah. And you'll notice they've got one working out their examples of working out how they give you the 5 marks, the diagrams they've drawn, which is similar to mine. Yes. And the one method is the similar triangles as they put here. And I hope you find my answer clear enough. And otherwise you can have a look at the mark scheme and work out an alternative solution to proving it. Okay, so that's question 17 done. The first part. The second part is the continuation of this. 17 part B is now looking at the forces involved in circular motion. So it's showing you the same model aeroplane or another model aeroplane attached to a wire that the girl is holding. So the tension in that wire as shown. Okay. Then gives you some more information. The aeroplane moves in a horizontal circle of radius 28.5 meters. So just to reiterate that, we can make sure we got the information clear in our head when we're reading the question. This is called active reading, and it's moving at a speed of 22.5 meters per second. So again, checking that the units are in SI units. A lift force acts vertically upwards on the plane, and the lift force is equal to twice the weight. So it's L equals 2W. So I've drawn that on the diagram. So that L is 2W. The weight is obviously down. So the resultant force upwards, yes, the force resultant upwards will be 2W minus W, which is also equal to W. Okay, so the force upwards, and then you've also got the tension, which is towards the girl's hand. Okay, so what do they want us to do? They've given you the mass of the plane, so that means that you automatically can work out W, yeah? And if you know W, you know the resultant force vertically. Okay. So what do we need to do next? So they want you to say that it says the wire will break if the tension is greater than 35 newtons. So you have to deduce whether the wire will break or not. So in other words, will T in the numbers that we've been given, using the numbers being given, be greater than 35 newtons or not? That's what we want to do. Well, vertically, we know the weight is mg, we know the lift is 2w, we know the resultant force upwards is therefore mg, which is equal to 15.2 newtons. Okay, so the upward force resultant is that. This horizontally we know is circular motion, so centripetal force is mv squared over r. We know m, we know v squared. Sorry, we know m, we know v squared, and we know r. So you put the figures in, you get 27.5 newtons. So that's the second force we worked out. We then also know that the centripetal force, yeah, and the horizontal motion make a right angle triangle with a tension. So the easiest way to do this, doesn't require any resolving, is to use Pythagoras. So I should have put, using Pythagoras, you have a right angle triangle, one force is centripetal, the other is a resultant force upwards, which is why it is, the lift is causing it, the wire to be held at an angle to the horizontal. Okay, so we don't have to work out that angle, but if we wanted to, we could, because t squared is 15.2 squared multiplied plus 27.5 squared, and then square rooted. Okay, so it comes out t is 31.4. Then you say, well, t 31.4 is less than 35, so the wire shouldn't break or won't break, and there's your fourth mark. Okay, that's fourth mark for here, and the first part was 5 marks. That is question 17 done. Question 18 is about charging a capacitor. Okay, so the circuit's been given, the resistance value's been given, and they want you to work out eventually the capacitor the value of the capacitance that you're using. Okay, so it tells you what the student did. So we know the circuit now. Here's a graph of the results. The student closed the switch to charge the capacitor and started the stopwatch. She recorded the voltmeter reading V every 10 seconds as the capacitor charged. So it's charging from 0 all the way to the maximum. Hasn't reached the maximum yet, because normally it takes about 5 time constants, I believe, to get to over 99% of the voltage that you're charging it with, which is shown here as V0 would be the maximum voltage, is the voltage of the battery at 6 volts. So basically what's happening here is you've got Kirchhoff's second law. The voltage is shared, the 6 volts, between the capacitor, initially at 0 volts, yeah, with the voltage across the resistor. So the voltage, or the EMF V0, must be the voltage of the capacitor plus voltage of the resistor while it's charging. Okay, as it charges up, obviously VC goes up and VR goes down, because together they've got to add up to 6 volts. Okay, so that's what's happening electrically. And here I've already drawn some lines on here. I've put them, the V0 is 6.0 volts. I've actually worked out where the time constant is as well, and I'll explain that later, because there's 2 ways of doing this question. So for charging, the equation is not given to you on the equation sheet. The discharging is, and that would be V naught e to the minus t over RC. So if you look at your equation sheet, you can see that they give you a discharge one, but this one is charging, so we have to consider what we know about charging. Okay, well, charging is the opposite of discharging. This time it starts, the voltage goes up quickly, yes, and after a time constant it will reach 63.2%, which is the opposite of 1 minus 36.8%, yes, or 100 minus 36%, 100 minus 36.8% of the total value. So that's what I did. I looked at what is 63.2% of V0, and it comes to about 3.8 volts. So at that point, we know that we've got the time constant, because that will help us, and it's a shortcut to the answer. But I'm going to do it using this equation first to show you how it can be done. Now, according to the syllabus, you do need to know about charging and discharging capacitors, but this equation is not given to you on your equation sheets. If you want to use it, you have to remember it, or you've got to be able to work it out. Okay, so that's the first part of question 18. And then it wants you to part A. So this is why I put the asterisk. Sorry, just move it down the screen. So part A, I put an asterisk there to explain there's two methods to do this. Determine a value for capacitance. So if you're doing a charging equation, it's that. V equals V naught 1 minus E to the power of minus T, which is time constant, divided by the resistor, which we know, and the capacitor that we want to work out. So we know this is 6. E is a special number, which we know. T we can work out from the graph if we wanted to, because that's a quicker way of doing it. R we're given. Okay, so if we take from the graph a value, a second value, you need a pair of readings to be able to use this equation. So I've taken the value that the examiners are using, which is at 70 seconds. They use 70 seconds because it gives them an answer of 5.1 volt. Okay, so I think that's why they're doing 70 seconds. I'm just checking that that's what they've used. Yes, they use 5.1 volts. So the value here is 5.1 volts. So you need to take corresponding values from the graph, take a pair of values from the graph. So I've done 70 seconds, 5.1 volts. You get a mark for doing that. So we're going to use the charging equation. And if you substitute the numbers correctly into the charging equation, you will get this. And they want you to make sure you used V naught as 6.0 volts. Okay? So, because if you look at the graph, it actually doesn't go up to 6.0 volts because they haven't charged it fully. But it will get to 6.0 volts. The students stop taking readings. So if you continue, eventually it will get to 6.0 volts. But it will take longer than the time shown, which is 120 seconds, which is about 3 time constants. Okay, so when you put the numbers in, then obviously you can rearrange it. You need to know how to take log graphs. So you want to make sure you put this value in, 5.170. We know the resistance, so the only thing we don't know is C. Then they want you to take logs eventually. So I've just moved the equation around to make this part of it the subject of the equation. Okay, sorry about the confusion there. I was rewriting the same equation again once I found out that I wanted to go to another step first before I did the logs. So once you do that, you'll see it's 1 minus this fraction, which is 0.85. So you get 0.15 on this side. Yes, it's basically that's equal to 0.15. But when you take the logs of 0.15, you will have both of them negatives, so the negatives will cancel. And the only unknown is C. So 70 over this fraction is equal to 1.9. You can cancel the negatives, and C is then rearranged to give you a value of 2.19 times 10 to the minus 4 farads, which you could round up to 220 microfarads. So that is using the equation for the charging. If you don't remember the charging equation, you can go back to my graph. Yeah. Look at how I know that obviously discharging, one time constant it would discharge to 36.8%, because obviously discharging it would be steeper at the beginning. In charging, in time constant, you'll go to the 1 minus of that, just like here you've got a 1 minus, and it will come to 63.2% of V, which is 3.8 volts. So at 3.8 volts, I'm looking to see the time constant is approximately equal to 38 seconds. Now, this is not as accurate as using method 1, but it is a quicker one. And if you don't remember the equation, then this is the way to solve the problem. So if you're doing that question, I have done it at the bottom of the sheet here. So shortcut to method A. RC can be found on the graph. Yes, for charging, time taken to reach 63.2, which is 3.792. You get that, RC is that, then you know R, you know T, so you just put it in. So this is T equals RC, so T tau equals tau equals RC. So there is the tau value. Just change the subject, make C the subject, and it comes to 226 times 10 to the minus 6 farads, or 226 microfarads. So if you compare it with my first method, the difference is 226 to 220 microfarads. Both of those should give you full marks. Okay? So obviously this second method, I think, is easier. Because I don't think they should be asking for the calculation of a charging of a circuit with the equation, because it's not in your equation sheet. But if you remember it and you know it, you can use the method I've shown for the first way of doing it. Then it wants you to sketch on the axes below how current in the circuit would vary. The current, obviously, when you're charging or discharging, initially the current will be high when the capacitor is uncharged, because it's easy to push charge in when the capacitor plates are not charged at all. As they get charged up, they'll actually resist more charge coming in, and they'll slow down the rate of charging. So that's why it will be a logarithmic shape. So this is the exponential shape, will get you 1 mark. And to work out the maximum current, it wants you to work out the maximum current is when there's no resistance by the capacitor. So it's basically all the resistance is due to the resistor. So at that point, the capacitance is not really taking part. So it would be V0, which is 6.0, divided by the 168 kilo ohms, and you get that the maximum current at the beginning will be 3.6 times 10 to the minus 5 amps, which is 36 microamps. And that's at time t equals 0. So you get 1 for putting that in, 1 for showing the shape there, and 1 for doing the calculation. So that's your 3 marks. So as you can see, these questions do become longer, which is why I didn't want to do it in one video. Part B then goes on to say the student then connected the second 168 kilo ohm resistor in parallel with the first resistor, and then once this is explained how the time taken to charge the capacitor would change. You do not need to do any calculations. There's no further calculations required. Well, if the resistance in total would decrease, because whenever you add a parallel path in a circuit, you're actually increasing the current. So the current would increase, and therefore, if the current increases and the resistance is decreased, so R has gone down, capacitor hasn't changed, so RC would decrease, either of these for the second mark, one of these for the first, and therefore the capacitor would take less time to charge. Okay, you need to make sure you're explaining each part of it very clearly. Okay, sometimes the examiners do make a mistake when they're reading through your questions. I saw one of my students' answers, because you can ask for your paper to be sent to you so you can go through your mistakes, and I think they mismarked it, and she could have got an extra mark for her question. Okay. Right, question 19 is about auroras, yeah, and they occur in the north, near the North Pole or the South Pole. So the Aurora Borealis and the Aurora Australis is the one down, is seen from Australia. When charged particles collide with gases in the atmosphere, they create these lights. So these collisions produce tiny flashes of light that fill the sky with light. I once saw them when I was a teenager, all the way down in South England. So it can, when they're active, they can actually be seen in further south than the poles. Obviously, the closer to the poles you are, the more often you'll see them. Okay, so collisions between electrons and oxygen atoms cause the emission of green light. They're telling us that. So this is revision of Unit 2, spectra. Yeah, electrons getting excited and then de-excited is what gives off the green light. Calculate the velocity of the electrons that would cause green light of wavelength 560 nanometers to be emitted. Well, we know, if we know the lambda, we know the frequency, so we can convert the frequency, and therefore we know the energy corresponding to the emission of green light automatically by using the E equals HF equation. I've rearranged it to make it E equals HF into E equals HC over lambda, so I can do the calculation in one go. But you'll get 1 mark for working out the frequency, and you'll get 1 mark for working out the energy. So I just put it all in one equation, so it just saves me time. Then once we know the energy involved, that must have been supplied by the kinetic energy of the electrons colliding with the oxygen atoms. That collision is what excites it and then de-excites it. So that's the assumption, at least. Once you do that, you'll see that the kinetic energy of the electrons, half m electron times v electron, velocity of electron squared, is going to be equal to this energy you calculated. So now you need to change the subjective equation. V squared will then be 2 times this energy divided by the mass, and if you want to get at V, you just take the square off and you make that into a square root. Once you do that, I calculated this before, it's 8.83 times 10 to the 5 meters per second, and that should be your answer. I think you can give it to 3 significant figures. Let's see what the examiners have done. They've put it down to 2. So 2 or 3 significant figures would be my suggestion, because here you've got 3, here you've got 3, here you've got 2, so 2 could be possibly the correct way of doing it. Okay. And then the next part is a little bit more reading to do. So it says radio waves are also produced during an aurora. So it's giving you information about how electrons moving in a circular path in the atmosphere emit radio waves. So if electrons are moving in a circular path, you know that's acceleration of charge. Whenever you accelerate a charge, it does actually produce electromagnetic energy. So frequency of emitted radio waves is the same, it says, the frequency of the emitted radio waves is the same as the frequency of rotation of the electron. So it's telling us that, well, if we know the frequency of the rotation of the electron, we know it's 1 over period. So this is the kind of information that I'm storing in my head when I'm working it out. And if it's a circular motion, and we know the velocity is given to us in the next paragraph, the velocity is 2 pi r because it's circular motion, circumference divided by the period. Okay. Once we know that, we can convert that by getting rid of the period and putting it into a frequency equation. Okay, there are different ways of doing this. This is a circular motion, so we need to analyze it. It says the speed is 1650 kilometers per second. You've got to change that in meters per second. Yeah, easy to make that mistake. Is moving perpendicular to the magnetic field, B, with a magnetic flux density of 48 microteslas. So it's 48 times 10 to the minus 6. So these are the ways that student can lose marks, is by not converting the kilo and the micro to the correct values and therefore lose marks. It then says the radio station is broadcasting at a wavelength of 220 meters. So if you know the wavelength, you can convert it into frequency if you wanted to, because you can either also either work out frequencies or compare wavelengths at the end, because we want to know whether the radiation emitted by the electron, so going in a rotation, would interfere with the signal from the radio station. So if they're about the same wavelength or about the same frequency, then interference will occur. Okay, so this is also revision of Unit 2. Okay, so circular motion tells us, so it gives you a clue, you should calculate the radius of the circular path. Well, how do we do that? Well, we know circular motion tells us that BQV, the force, centripetal force for a magnetic field, is equal to mv squared over r. One of the v's cancels out, so you can come up with the equation where r is momentum over bq, which is a common way of using this. This comes in every exam, I think, that you need to make sure that you can equate these two. So you'll get a mark probably for showing you can do that. So once we know the radius, it put the numbers in correctly, you changed it to the kilometers into meters, the microteslas into the correct form, and then you got the data from the data sheet for the mass of the electron and the charge of the electron. So these are from your data sheet. Come up with 0.196, you'll get a mark for that. Then you want to work out the frequency of rotation of the electrons. So remember what I told you at the top of my page. So I already worked out that we need to know the circumference and the period, or you can change that to get rid of the period that way. So I've done it straight using V equals 2 pi RF. So I put V equals 2 pi RF as being equal to the other way of doing it, so you can have a look at the mark scheme should you get your hands on it, if you can get your hands on it. So frequency is equal to the velocity that we're given divided by 2 pi r, and we just worked out r, so you just got to make sure you don't forget to multiply by 2 pi. Believe it or not, I've had students lose marks just because they forgot to add the 2 pi in, and you come up with a frequency of 1.34 megahertz. Okay, so that's the frequency of the rotation of the electrons. So I'm comparing frequencies. I'm not bothering to go to the wavelength. I'm then converting the wavelength. I could have done the other way. I could have converted this into a wavelength. So I've done the frequency of the electrons. So I'm now going to change the 220 meter wavelength into a frequency by using C equals F lambda, where C is 3.0 times 10 to the 8, speed of light, speed of electromagnetic waves, and divided by 220, which is that, comes up to 1.36. That was 1.34. So both frequencies are almost the same, so interference is highly probable, and this would therefore cause interference. So I don't know whether you should put highly probable. I would just keep the English simple and say would cause interference, because they're approximately the same, and any variation could be due to uncertainties in the data. Okay, hope that makes sense. That's question 19 done. Okay, hopefully this video we will be able to finish it in one go. So question 20 is looking at particle physicists and the principle of conservation of momentum when analyzing particle interactions. So usually particle interactions means a collision. In the case of momentum, says the state was meant by the principle of conservation of momentum. I had one student who put momentum before equals momentum after. They lost one of the marks. So you have to put total momentum before a collision equals total momentum after a collision. You need to make sure you got that examiner in front of you and you slap him across the face to make sure he doesn't take off any marks. Treat him like he knows nothing. It must be the total momentum. Before what? Before a collision. So don't leave any gaps in your thinking, provided no resultant force is acting on the system. So in other words, you have an isolated or a closed system. I would put both of these points in. Always drive the point home. Yeah? So then, that's how you get the first 2 marks. Silly to lose those marks. Okay? You just got to get into the habit of expressing things explicitly. Don't leave anything implied. The cloud chamber photograph below shows alpha particle tracks in helium. Okay? So there must be helium inside the cloud chamber. An alpha particle collided with a helium particle at x. So x is here. So we're assuming that the alpha particle is coming this way because afterwards it says the collision. After the collision, so here's the collision, the alpha particle moves off at an angle 20 degrees to the initial direction. So the initial direction is there. So this is, it looks pretty much vertical, this dotted line. So alpha particle comes in vertically and then it gets deflected to the right, and therefore something else gets deflected to the x, so that must be the helium atom that was stationary. We're assuming the helium atom was stationary to start with at x. They haven't said that. Okay? It says alpha particle collided with the helium at x. Okay? After the collision, the alpha particle moves up 20 degrees to the initial direction as shown. That means the other particle must have moved 70 degrees to the left. Okay? So this is a very easy way to solve the problem. So they want you to show that the speed of the helium nucleus immediately after collision is about 5.6 times 10 to the 6. Sorry, still haven't got it all on the screen. Show that the speed of the helium nucleus immediately after the collision is about 5.6 times 10 to the 6 meters per second. That's what we've got to show. So in the diagram, that's the one that's going off to this side, 70 degrees. Okay, so I've put resolving horizontally or at right angles to the initial momentum because it doesn't actually say that it's vertical. So resolving at right angles, the total momentum left and right at the beginning was 0. So the momentum of the alpha particle to one direction, so I put it to the right, that's what my arrow is showing, is plus the momentum of the helium atom to the left, that's the one at 70 degrees, must add up to 0. So if we now put in the values which are given, yes, all over there, we don't put in this value, we want to show that the helium there They want to work out V helium. We know the sine of the angle is the resolution, because it's the angle to the vertical. So to go horizontally, it will be sine of the angles. Both of them will be sine. This is the momentum of the alpha particle, the velocity of the alpha particle. Now, if you remember, the mass of the alpha particle is a helium nucleus, so both masses are the same. So you can actually cancel the masses. That will save you some calculation time. And then you put the numbers in. I nearly forgot to put 10 to the 7 when I transferred it to the next line. So it's the ratio of the two signs is what gives you the answer, and it comes to 5.64 times 10 to the 6 meters per second. Yeah, so that's approximately equal to 5.6 times 10 to the 6 meters per second, which was what they wanted us to show that it was. Okay? Make sure you put that last bit in that I've just added in red, because they could be strict and penalize you for not doing it. Okay, the next part. The kinetic energy of the alpha particle before the collision was 9.0 times 10 to the minus 13 joules. So that's the total kinetic energy before. So we're assuming that was a total kinetic energy before, because this question assumes, I put at the bottom, that the helium nucleus initially has zero velocity, therefore zero kinetic energy as well. So for elastic collisions, the total kinetic energy before must be equal to the total kinetic energy after. You then put in the total kinetic energy after. They've both got kinetic energy after. This time you need to put the mass in, multiplied by each of the velocities. I put the accurate value, 5.64 from above, and then we were given 1.55, so I put them both to 2 decimal places. Squared them out, put them in the calculator. One comes to 1.06, the other comes to 7.98. Add them up, it's 9.04. Well, 9.04 is approximately equal to 9.01 within the tolerance of acceptability. So the total kinetic energy before equals the total kinetic energy after. This sigma sign means sum of. So it's approximately equal, so collision is elastic. Okay. One student forgot to square one of the velocities and therefore got the wrong final answer. Simple mistakes, easy to lose marks. Okay, here, the next question, 21. It's the last 2 questions to go, so bear with me. Remember, when you're listening to it, you can speed up to 1.5 because you'll absorb the information better, in my opinion. Modern kitchens have induction cookers. Yeah, the idea of an induction cooker was first suggested more than a century ago. Okay, because obviously that's when Faraday did his work. Yeah, Faraday, electromagnetism. An iron kettle was heated by passing an alternating current through a coil wound round a soft iron core as shown. So the soft iron core, if you like, also is part of the heating effect. And it tells you that the iron kettle, so the kettle is made of iron. Okay, so it's a conductor, and so is here as a conductor. So you've got iron kettle, iron core, and here you got the coil. Okay, so explain why the kettle heats up in effect when there is an alternating current in the field. Well, any current produces a magnetic field, 1 mark. Alternating current produces an alternating or varying magnetic field, 2nd mark. Okay, there is a constant change of flux linkage within the metal kettle, or you could put the core, the iron core also. So there is a constant flux linkage within both iron materials due to the alternating current or field. Yeah, or words to that effect. So this is another mark for this point, and therefore an EMF is induced across the kettle or the core. Okay, so we got 1, 2, 3, 4. I'm looking to see where the 6th mark is coming from. And then current is created, which in turn has a heating effect. So if you've got an EMF in the kettle's made of iron, core's made of iron, they both get hot. A current is created, which in turn has a heating effect. Yes, because of the resistance I squared R. So I'm just looking at the mark scheme to see what point I have missed from the mark scheme. So as long as you're explaining this clearly we're in question 21, just looking for it. Okay. So here's the content that they're looking for. Obviously, the way you write your answer can also gain you the marks. So any of these points you can get, but the answer must also show a coherent and logical structure with no confusion. Yeah, so lines of reasoning demonstrated. So they give you 4 points for listing these things. I just tend to do that because I know if I've got all these points in the clear logical format, then I've probably got the 6 marks anyway. So current circulate, the kettle heats. Oh, okay, so my last point, EMF is induced, yes, was the 4th mark. Then the current is created, circulate in the car, so current is created, that's 1 mark. And then the 6th mark is, which in turn has a heating effect. Yeah? Yes, so this is 2 marks, this last one. Or you could put the iron core gets hot, the iron core also gets hot, and then conduction also is part of the process. So it's basically how you decide to write out your answer, which will get you the marks. Okay, that's 21 part A. 21 part B is then they've got half a metal pan here. Manufacturer demonstrate the use of an induction cooker using a raw egg, yes, so this is also part of the raw egg, and a steel frying pan that had been cut in half as shown. So steel pan, induction area, egg. The cooker surface is not an electrical conductor. They're usually they're made of glass, aren't they? If you've got them if you've seen them in your own kitchens or in any kitchen. And it says the cooker surface is not an electrical conductor. So why they're telling you that? Explain why the egg cooks only when it's in contact with the pan. Well, the cooker surface and the egg are not conductors, so no heating effect, no current or EMF is induced in non-conductors, so that's 1 mark. But the metal pan is a conductor, so it gets heated as current is induced in it, so only that half of the egg, yes, if you want to just spell it out, so only that half of the egg gets cooked. Okay, that's your 2 marks. And finally, question 22 is about subatomic particles, yes, and strangeness. So many subatomic particles are unstable and have only been detected in high energy particle collision experiments. So they get created at high energy. They're unstable at when they don't have high energy, and they decay into something more stable. Kaons are short-lived subatomic particles of such. Okay, they are also known as K-mesons, and were the first strange particles to be discovered. So if they're first strange particles discovered and they're giving you information table with strange in it, that means that this K particle must have a strange quark in it. Okay, that was a 3rd quark to be discovered. The following table lists some quarks and their charge. Okay, now I've also put the anti-quark because I automatically know that mesons must have a quark and anti-quark combination. Okay, so this is information that I'm gleaning from the question already. Explain the quark structure of a K- meson. Well, if it's a K- meson, we know it has to have the strange quark in it, so you automatically know it's got the strange quark in it. And it says a K-, so if it's minus, must contain a strange quark and must have a total charge of -1. Yes, so we know that. So we know it's S, so how can you get a -1? Well, you need a quark. Mesons must also contain quark, anti-quark, as I've mentioned before. So you want an anti one of these, and the only way you can get a -1 is to have a -2/3 added to it. Therefore, it must be an anti-up, so it must be strange anti-up. And this will allow you to show that you fulfilled all the criteria. Okay. Then it says, the mass of the K-meson can be represented using mega electron volts. Okay, don't worry about the c². Basically, they're talking about mega electron volts as opposed to joules, and the fact that they put divided by c² is because m is E divided by c² in Einstein's equation. So they're just showing you that it's a mass they're talking about rather than an energy as such. But as you know, mass and energy are equivalent. So you first got to convert mega electron volts into kilograms, but by going via joules. 1 electron volt is 1.6 times 10 to the minus 19 joules, because it comes from the equation E equals QV, and you need to revise that if you don't know. So whenever you got mega electron volts, you simply multiply 494 times 10 to the 6 shouldn't say 16, I don't know what that line is, 10 to the plus 6, multiply it by 1.6 times 10 to the 19, gives you an answer of 7.90 times 10 to the minus 11. They're giving you 3 significant figures, so we want 3 significant figures there, and joules. Don't miss out units, even in interim calculations. You then want to work out the m. We know the e is here, so we put the e in there. M is e over c squared, and you get 8.78 or 8.8 to 2 significant figures. So this or this for the final mark. Now, the next part of the question is about a cyclotron. Okay, these are very, very common questions in Unit 4. So the structure of a cyclotron, see, it starts at the center and then it kind of spirals outwards, gets faster, but also travels a bigger distance. Okay, so that's how they work. And it's got 2 Ds, as they say. Okay, and in between, you've got an alternating current, which gives it a kick every time it goes from one D into the other. So they want you to explain how the cyclotron produces a beam of high energy particles. Okay, so in other words, how does it accelerate them and how does it work? You should refer to the alternating potential difference, yeah, and the magnetic field. Well, alternating potential difference accelerates particles as in they gain in kinetic energy. Because remember, acceleration is a vector quantity, so it could be acceleration due to a magnetic field or an electric field. In the electric field, the acceleration leads to a gain in kinetic energy, therefore a gain in velocity. So you get 1 mark for explaining that. You get a 2nd mark for explaining that magnetic fields accelerate particles in terms of direction rather than kinetic energy. And it's due to circular motion because the force, the centripetal force, is always at right angles to the direction of the particle's velocity or motion. So this is a lot for 1 mark, but you don't have to say exactly as clearly as I put it. As long as you're making that point, you can look at the mark scheme later on, but due to the length of this video, I'm going to try to speed up. The magnetic field force maintains circular motion whilst in the Ds. So in the Ds, the magnetic field is just making sure that it's going in the circular motion continuation. And then the potential difference, AC, polarity switches every half a cycle to give an accelerating force between the 2 Ds. So between the 2 Ds in the diagram as I showed you before, that's when the acceleration in terms of gaining velocity happens here and here. Yes, because it's going this way around, as you can see, because it's exiting here. So each time it goes between the Ds, the frequency of the AC is such that it's timed perfectly to match the velocity of the particle as it transitions between the 2 phases. So this every half second, every half cycle, it changes the polarity, and it's just at the right time. So the additional 5th point that you could get the 4 points from, so if you missed one of these before, you can just say the potential difference has a constant frequency in these cyclotrons, where the period which is independent, frequency or period, is independent of the speed of the particles. Basically, it's been designed so as the particle speeds up, and it has a bigger distance to travel, so they've made it just right, so each time it crosses from one D to the other, it speeds up, and that's how you get a high energy beam of particles. Okay, so any 4 points from the list I've shown you. And finally, to the last page of the exam, you'll be pleased to know, or at least I will be pleased to know, so I can then go and have a cup of tea. Right, the first cyclotron was invented or made by Lorentz in 1929, and his cyclotron was able to produce a beam of protons, with a maximum kinetic of 80 kilo electron volts, which is much, much lower than what we use these days. So that's the maximum kinetic energy. You can convert that into joules, yes, which you need to do for later on. Calculate the magnetic flux density, yes, of the magnetic field used with the cyclotron. So they're giving you the diameter of the cyclotron as 0.11 meters. So the radius, maximum radius of it is 0.055. Because remember, circular motion means BQV equals mv squared over r. So it allows you to have the equation we used before, which was make r the subject of the equation, but this time we want to calculate b, so you should use b as the subject of the equation using this. So it's a very common question to equate BQV with the circular motion mv squared over r. In this case, b is the momentum of the protons, in this case, divided by the charge, divided by the radius of the cyclotron. Okay? So once you do that, the other thing you know, once you've got the Once you got the energy, you can work out the momentum, because remember that this equation is a shortcut. Yeah, it's basically a way of changing between momentum and energy. In this case, we want to work out P, because we know the kinetic energy already is given as 80 kilo electron volts, which we put in joules. So we don't know P, we do know 2, and we do know the mass of protons from our data sheet. The mass of the proton is here 1.67 times 10 to the minus 27 kilograms. So if you change the subject to the formula from P squared, you can make P equals 2 times the kinetic energy multiplied by the mass, square root that, put the numbers in. There's my 80 kilo electron volts multiplied by 1.6, the conversion to get from electron volts back into joules, divided by the, multiplied by the mass. This is multiplied, just run out of space, so this says here multiply. So you multiply all these numbers together and you'll come up with the momentum. Once you know the momentum, you can then use this equation. Yeah, the momentum is given from here, so that's mv is 6.54 times 10 to the minus 21 divided by q and r, which you make sure you have worked out from the diameter of the cyclotron, and then you come up with 0.743. And how many significant figures do you think we should use? I think you should only use 2, because we have 80 kilo electron volts, 0.11. We're not really being given any accurate data, so it should only be 2 significant figures. You could lose a mark if you put 3 significant figures here. Okay, that's the end of this video. I hope you found it useful, and I hope I explained it clearly. So remember, I will be doing more videos as time goes on. So please make sure you've subscribed so you get notified. I think you also have to click that bell notification. I don't really know, because I don't really subscribe to anyone's channels, but I believe that's what you've got to do. So also please like and share it, because if we get enough viewers, I will continue this service from year to year. If we don't get enough subscribers, it doesn't really make it worthwhile, because it takes quite a lot of time to write out these model answers. Anyway, thank you very much, and hopefully see you in the next video. Bye.